Thank you very much, Mr. Chairman, for this warm and also very exact introduction. I think if looking into this audience, you are the electrons, and the holes have been gone to information, as I understand, defense and security, and to emerging research. So I'm very happy that the electrons representing the energy have stayed in this room. My title, exactly, I do not remember who fixated it in the end. Was it me or was it the organization? It's rather broad and in a way encyclopedic, but I think it very well serves the purpose of congratulating you all to the 70th anniversary of CSIR. And this congratulations is not only from my side, but it's also from the side of the Fraunhofer Society. It is in some sense similar to the endeavor of CSIR in somehow moving up basic research to industrial applications, and as your deputy minister said earlier, to create value. And you see that our society is broken down in around 66 or 67 institutes by now, spread all over the country. And you see in this little graph how we try to go from basic research, which is done in other societies, like the Max Planck Society, where I was a member when I did nuclear fusion, as was already said, and we are somehow there in the middle between academia and the industrial research. The society encompasses 22,000 employees by now and has an annual revenue of €2 billion per year. We are one of those institutes, and also our institute wants to congratulate you to the 70th anniversary. This is a short picture of what we are doing. And we in Kassel, we are specializing on the energy system technology. So it is not photovoltaics, it is not wind, it is not electromobility, it is everything that is between those. It's always a little difficult to understand what energy system technology is, and I hope I can make it clear in the course of this talk. So as I said, my title was pretty encyclopedic, The Future of Energy Systems, and therefore, let me ask you a question. I understood now that South Africa wants to go in the direction of renewable energies, and we did so also in Germany, but I want to ask you, are you really knowing what you are doing? What the difficulties are that you are facing and that you have to overcome? And you need a motive to do so, and therefore let us work for just a brief moment on the motives. And in order to do so, I want to somehow systemize the options that we have. What are, for future energy systems, the options? What motivates us most in our institute is the climate change. And I brought here the photography of the polar cap in September 1979. And I have to admit also, I'm for the first time in South Africa, and also for the first time on the southern hemisphere. And I rather had brought a picture of the southern pole, so I apologize for that. But this is our perspective, and this ice cap changes. And this is a picture from 2007, and I flip it back and forth, and you see what happens. So the polar bear has no home any longer, which is sad. And also, we in Germany at the south, we have a very spectacular mountain range called the Alps, and we do skiing there and also do the Swiss and the Austrians. And more than that, they sell the service, the ski tourism, all over the world. And now this, what you see here, it causes a big problem for that industry. So what options do we have to change this picture? Now, we do some basic physics at first. So look, first, what are the sources of energy? And the sources are cosmic in a sense. And if we narrow it down, there are solar sources. There are sources that we find on Earth. And we take these sources and we make a civil use to transform these primary sources into energy that we can use. And then by doing so, we do something to our biosphere and atmosphere, and that's where we have to assess whether this is a viable energy system or not. So I indicated with this number here, I see 4 large options where the source is. So the first source I want to talk about here is where the sun is the primary source, and the sun burns elementary fuel, which is just the proton, and fuses it into helium, deuterium, and then it somehow cooks every other element that we know until iron. And by doing so, the sun emits radiation, and then this radiation does something on our Earth. It had changed over the course of 1 billion years the atmosphere from a CO2-rich atmosphere into the atmosphere as we know it today. And then the radiation takes the CO2 and water, and it synthesizes hydrocarbons from it. And by some processes, geological processes, it presses those down into the ground where we find it. That's why we call that fossil forces. They are somehow to be found in the ground. And then we make a civil use of it by just burning these fuels. And again, we release the CO2 and the H2O in the atmosphere. And we call all that the fossil age. So the first persons that the deputy minister talked about hundreds of thousands of years ago in Africa and East Africa, they used a biological form of this, and then later the oil was found constituting this fossil age. And it's only very recent, we can say historically, that we realized that CO2 is not only a very important substance that goes into our biological matter, but it also controls the radiation influx into our atmosphere, and thereby it is a very delicate control element, which is very important, but if we do not do the control right, we run into a problem. That's what we realize today. Then we have a second path here, which is truly cosmic in a sense. As I said earlier, that the sun boils the chemical elements until iron. But that's, in some sense, is a minimum, and you cannot go further in a star. So the question is, where do all these heavier elements stem from? And they stem from a very exciting event that at the end of the life of a star, the star implodes and explodes, and there's so much energy, fusion energy released there, that it can form the heavier elements. So then these form dusts in the cosmos and somehow assemble in solar systems and finally find their way also into the ground. So in that sense, burning uranium is also a fossil age, if you want. So we call that the fission age. Let's say we have a civil use of that in an atomic reactor, and we are bound to the physics of nuclear fission, which produces these chain elements where we cannot alter very much, and we assess as being harmful to the biosphere. There's also an aside there that the geothermal energy that's inside our planet may also stem from fission processes. So there's a third route, which is all, again, cosmic in its origin. That's the light elements that were born in the very early stages of our universe, and amongst them, deuterium and lithium. And that's where the researchers of nuclear fusion, where I was one from in some part of my life, tried to get the energy out of by now fusing these light elements and somehow releasing helium. These experiments are still underway, and there are some slight impacts on the biosphere, which is thought maybe much smaller than this here, which is called nuclear fusion. So our assessment here, it is not available yet, and my personal estimation is that it won't be available as something that you can regularly use in energy processing within the next century. So we have a fourth path, which is very similar to this one, as again, the sun is our source, and now we use the same fusion process, but we take the radiation directly, either by using the photovoltaic process, by converting radiation into electricity, or by using the whole atmosphere by turning around this energy and turning it around until it generates winds and waves, and also precipitation that could be used as hydropower. So we arrive at these variants of solar radiation: photovoltaics, wind, hydropower, solar thermal, and biomass. And the question is, what name should we give this age, which is just now to start? And I think it's fair to say that let's call it the solar age. Now we all are entering the solar age, and we have to ask ourselves, what is the price for that? So, but first, before we now go into that, let me make one remark here about the geothermal energy. So this is our Earth, and we do not know too much what is under our feet. We know much better what is upward in the skies. But I ask you a question. If at our present use, we're using 400 exajoules per year, which is 4 with 20 zeros, and this is the primary energy consumption globally, what would you think, how many years this would reach out to cover the world needs every year? So just some opinions from your side. Is it in the hundreds of years, or the thousands of years, or is it even more? What would you guess? But just cooling down the inside of our planet. So I do not want to torture you. You can figure this yourself. It's very easy math. It's 160 billion years. 160 billion years. It's more than we think that the universe is old, as we think the universe is something like 10 billion years old, and it's also much longer than our sun will exist. And I have a friend with a research union that we are part of, who is geologist, and every once I meet him, I ask him, why is it so complicated to drill just 30 kilometers down into the ground? And he always refuses an answer to this question. So there's lots of energy, very close, but unreachable. So coming back now to this one option that remains, and that I think is so important if we go into a political discussion, and that's why I made this deviation here in the beginning. It is truly, as we think, just the one option that we have presently to act on the climate issue. So what's the price for that? In Germany, we started an experiment, which we called the Energiewende. And Wende is a word that means turning around. And it doesn't specify whether you turn around 180 degrees or 90 or just a little. So we try to turn around, and it's not unequivocal. It's really a societal fighting on whether we should turn further or not. So what are we doing there? We started to introduce these atmospheric effects, the wind, and by now we installed almost 40 gigawatts of wind power in our country, comparing to an average load of 60 to 80 gigawatts. And if you look at this over time, you see that we are here in 2015, having arrived at this 40 gigawatt range here. And, no, wait a second, that's here. At an annual rate, 2 gigawatts per year, we have now increased that at an annual rate of 4 gigawatts per year. And this is how we think we should go. We should arrive at some 11, 12 gigawatts each year in increase. And you see the cumulated curve of that. So here we are at 40, as I said, and we should arrive somewhere there at 230 gigawatts. That's our target, let's say. And it is split up here in onshore and offshore wind, and gray means that's the repowering. So around here, we are ready with the installation, and then we are repowering the old plants. So the question is, it looks quite favorable here, but here somehow it's saturating, and are we politically willing to go on this gray curve is very much under debate presently. Now we come to solar. And with solar, the numbers power-wise are very similar. So we also say we have to go to the 200 gigawatt region to reach the 100% CO2-free target. And we are presently also at 40. So they are very similar in development. But what did we do there? Here in the diamonds show the actual development until today. And we have to jump up to 7 gigawatts per year installation rate. And then comes the repowering. So we ramped up to this figure in a very short time here, and then we ramped it down again. So maybe there are control engineers in this room, and they may ask, why do these stupid guys do that? When we ramped it up so fast, we caused lots of social imbalance. So there were these owners of the plants who were getting a good feed-in tariff, and then there was those who had rented an apartment and could not invest in this. And then the politics said, oh, we have to stop that. And that was the effect of stopping that. So what happened then, we destroyed our PV companies that just started. It's very severe. In our city, there is one, a big one, a world global leader in inverters, and they had to release 1,600 people. A neighbor of myself was employed there. So why do the people do this? It was probably too fast, but then this counter-reaction was also too fast. And what I want to say here is, if you want to copy our model, please do not repeat this mistake. These were the economical issues about our Energiewende, but we also have technical issues here. What is depicted here is a medium voltage area in the south of our country, and you see here the connecting transformer to the high voltage. And we monitor, over the years, the power flow that goes across this transformer. And what you see here is a picture like that. So look at first at this envelope here, which shows over 4 years how our load behaves. And you see that we have most of our electricity consumption in winter, and then summer a little less. And that flows in the direction down into this area, where those farmers mostly set up now lots and lots and lots of photovoltaics. And this is what happened through the years. That's feeding back electricity from here across the transformer into the highest voltage regime. And you see how this increases over the years. This is completely new. We never saw something like that earlier in a high voltage transformer. And of course, we have to think how we cope with that. So the main question I want to pose to you is, or to us also, do renewables lead to a reliable and an affordable energy system? So we can rephrase that by asking, can renewables provide security of supply? And you may also be familiar with this annual load duration curve, but let me just repeat. You monitor during a year the load power, and then you sort these events of load power each day, let's say, or each hour. You sort them by size. So here that shows the highest powers that we have in the system, what I already said, between 60 and 80 gigawatts. And that goes down, and these are lowest powers Sunday morning, where all are still sleeping, is here. And for each moment, you also plot whether the power came from a base power plant, a nuclear power plant, for example, or from a medium power plant, or a peak power plant, say a gas-fired power plant or hydro plant. And this is the picture that is probably also very similar for your country. I want to start with a redefinition, because people with this word base load start to confuse consumption and generation. And I would rather prefer to talk about about base power. So that's the generators that release the base power. So if we now introduce renewable energies, how does this picture of the annual load duration curve look like then? And you see it here. And if you toggle back and forth, you see that now this base load curve, if you may, base power curve, is steeper and lower. And that now here's already a substantial fraction of renewables. So, and if you increase this even further, so you see that there are moments here, and they have been reached now, where at some times during the year, a few hours, the renewables take it all. We are already on a par with our consumption. And so then this is what you would still call base power. Now, if we increase the contribution of renewables even further, then something strange happens. Not only that this triangle has gotten even smaller, but also that there may be times, again on Sunday morning at 8 o'clock, when there's storm and the sun is already up. Then we have excess power, and that is completely new to the system. So the question is now, how do we react to this huge fraction of renewable energies? And we do not need these base power plants anymore that are just driving down the road with a fixed speed. No, we need power plants that can react to this situation very flexibly. So, and this means, and this is, I think, and we think, important for your country as well, we do not see from a system point of view how nuclear and renewables fit together. It just does not fit. What we need instead are plants of this sort. These are gas-fired power plants. This is the flagship of the company Siemens where I was working. But they have to be different than they are today because they have to be future-proof, let's say. They have to live for 100 years even though we are working on them like mad, yeah? On and off and on and off and on and off, and that they should do it for a long time because these on and off stretches are so that they do not earn very much money on energy during a year. So the pricing of these plants have to be power-based rather than energy-based. So the question here is, will our system in Germany in the nearer future collapse under these installations? Here I depicted how large a solar field would be that could serve the whole country. And of course, it was not done in this way, but rather than this. You see the blue dots here, and it was even smaller than that. And you see that there's a blue haze of photovoltaic panels by now all over the country. So does our system collapse? We are very proud that we had the lowest outage minutes, at least in Europe, but I think even worldwide. So on average, there was 15.3 minutes outage time in Germany, and we even went below this number here. As you see here, the development, who are the bad ones? Okay, I do not know the names of those countries here, but it's also still very good, yeah. Now, we had a little natural experiment in March of this year. We had a partial solar eclipse. It was not a total solar eclipse, which is very sad. I hope you witnessed already or will witness a total solar eclipse. This is very spectacular. A partial solar eclipse is not very spectacular, but it gets darker. So everybody from the other side, let's say from the dark side, wanted to see that now the system would collapse due to the case that solar power would change so much. And we have 4 control zones in Germany, and the 4 are depicted here in blue, green, red, and yellow. And you see those curves is what actually happened during this 1 hour of the solar eclipse. And the dotted lines are what they prognosed. And you see that 2 of them, the green and the red, they were very, very precise on the prognosis. So it's really about the art of predicting regeneration, and that's a system issue. As I said earlier, what is energy system technology? One of which is working on the art of predicting the new renewable generation. And I can already hop ahead and say that we want to cooperate with you, and that's one of the arts that we want to develop together with you. So the second last question, will this new energy world be a financial disaster? We have already some financial disasters, as I showed you earlier, but will it be a financial disaster in total? We made the following calculation. We calculated that if we want to supply the whole country just on the basis of wind and solar, we would have and must have a mixture of photovoltaics, and there are some optimization criteria for this mixture. And it comes out that 3/4 energy-wise for wind and 1/4 photovoltaic-wise would be the perfect mix, if you want. And then there are some other contributions. And let's do the following easy calculation, that watt installed costs us €1. So we readily translate these figures into these figures. I still wonder why they didn't do it for the wind. Maybe somebody explains to me later. But you see, you translate gigawatts in giga-euro. Sorry for doing this. This is our abbreviation for billions, the American billions. We call it different, and our billions are a factor of 1,000 higher than the American billions. Yeah, sorry for that. And you have a price tag here for the generation technologies, but we also put price tags what should change on the load side. And on the load side, we have to insulate our buildings. This is probably something that you can spare yourself. But we also have the investments into the infrastructure sector, which is mostly the grids. We want that everybody drives electrically, and we try it out. I try it out presently with an e-bike. Yeah, it cost me 4 cents to go back and forth to work. We want that heating is done by heat pumps, and we want that we convert the excess energy into hydrogen, and even in other alkanes, like methane, for example, is for us the most attractive candidate. And if you sum all these hundreds of billions up, then we arrive at 1,500 billion euro. Again, this is a number with 12 or 13 zeros. Our gross domestic product in Germany is 2,600 euros, so this is a substantial figure here, but still the question is this really a lot of money? And we think, no, it is not. And let me see what I'm saying here. I will just give one argument. We have more arguments in this, but I give one argument why this is not a large number. We are in Germany a raw material country. Very much different from what I learned about your country. You have very attractive raw materials, and now you want to do the value add. We only do the value add in our country. We import mineral oil for driving and still, which is a shame, a little for heating. We import natural gas, we import hard coal, and we import also uranium. And all of which costs us 90 billions per year. Now you do this little calculation here. So 70 years times 90 billion already pays back the 1,500 billion. So now imagine 17 years on a perspective of investing into assets in the energy industry is not a long time at all. So the break-even of this financing is very close ahead. Yeah? One would be completely stupid not to invest now heavily to change this picture here. Okay, wonderful. So in conclusion, all of this is demanding a new architecture of this, let's call it the solar age energy system. And what are the features of this architecture? And I just read it out here to you. It's just a short list of those things that spontaneously I thought are important, but there are certainly many others here. So on the grid side, we in Germany will face mixed AC and high voltage direct current grids to connect, for example, the wind plants offshore, but also we think we need these corridors across the country to bring wind power into the southern part of the country. We need the system services like the power and frequency primary control and things like fault ride-through. We need it from the wind power plants and the solar plants because, as I showed you earlier, there are moments already in our system where we're completely relying on these renewables, and then they have to do the job of the system services. But we also need ancillary service from the distribution grid. What I also showed you is that the energy flow comes now from below. Yeah? So we have the solar power from below, and then the solar power has to provide the system services, but through all the transformers where the electricity has to squeeze through and provide all that. And having now this fleet of smaller plants, so instead of just a few large power plants, millions of small power plants, we need a management of this. And also all the protection circuitry has to be different. So we can say that the system operators that know their job presently very well, they're facing a new paradigm. So they have to have dispatchable loads and also dispatchable supply, which they already knew, and they have to follow a non-dispatchable load and a non-dispatchable supply. And we need all the smart technologies. And, I put it here as a second bullet point, we need new market designs. Because what you said, this error we made on the photovoltaics, this very painful error, could have been avoided if we had other market designs and regulatory frameworks already in place. Okay, I come to the conclusion. What we from the Fraunhofer Institute want to do together with the energy fraction of the CSIR is to somehow strike up a model of this changed world, of this future energy systems, what we call Kombikraftwerke. So it's already a combination that shows all the characteristics of the future, but say in a scaled version. And we call that, Stefan, please apologize to go over that so fast. You did that. So we say that renewable energies can contribute to this goal. They can solve the climate issue. They can be secure, and they are also economically. And here are the Kombi-Kraftwerk projects. We had a first project where we just said that we can scale up to 100% carbon-free energy system, and we already made a second project where we showed that also the system service issue can be solved by these types of new power plants. With that, I'm at the conclusion, and the conclusion is affecting your situation, and we envy you because your resources are so much better. So these are for solar. Stefan, you exaggerated here. I think it's just 900, yeah? Whatever you think that solar does in Germany, but I doubt. So we are less than that, and you are there. You can somehow prove whether your number is correct. So you're twice as large in full load hours solar. You don't have seasonal variations as we have. We have winter time, summer times, dark days and light days, and you're always bright. And then this is our wind resources onshore, and these are yours. And we pay 12 cents for solar and you 5.5. And for wind, we pay 9 and you 4.5. So your investment horizon is halved. It's just half of what we have. If our investment horizon, our break-even point, return of investment is something between 12 and 14 years. You do it in 6 to 7 years. And so you may think about whether you should still go nuclear. We have a price tag just recently, because you know there are not very many nuclear power plants built recently, but we have one now in England. And you know, it's an interesting story because it is built by France and financed by the Chinese. And the Chinese want that the English pay an amount that is somehow inflation secure. So we know exactly what they demanded from them, and that's what they pay for it. So we want to go to the Lords and the Parliament of England and talk to them and say, look at these numbers, yeah, and it's not local value creation. With that, I conclude. So we think that for a renewable future, the technical economical challenges of renewables are and can be largely solved. South Africa has an excellent wind and solar resource, so you have vast competitive advantages as well. The transition of energy systems makes sense, also economically. Next steps have to be the investigation of integration, both technically and market-wise. So a Kombi-Kraftwerk, South Africa, could demonstrate these capabilities in your environment. And from that perspective, South Africa has, again, two major advantages. The sheer size of your interconnected system, which helps with the aggregation effects, especially on the wind scale or wind side. And you do not have any seasonality of solar supply. So summer and winter gives almost the same output. The solar integration is therefore a pure intraday, intra-week challenge and not a seasonal one as with our country. So we have almost zero output in solar for 4 months each year from November to February with our present 40 gigawatt fleet. And for the 200 gigawatt fleet, I do not just want to think about it, what will happen in our country. So you can also invest into power to liquid to make competitive advantage of the solar wind resources, and you can make an export article for global carbon neutral fuels market that is sellable as a product. Thank you very much for your attention. I'll show you some beautiful pictures of